Hi, I'm Ian Rogers. I'm one of the actuarial science lecturers at the University of Kent. This short video will introduce some key ideas that you'll see in financial maths. You'll see these as part of MA 4513 in autumn, and you'll build on these in the spring term as well. But they're fundamental to the work of an actuary. They relate to things like, if I invest some money now or over a period of time, how much money will I have at a future date? And that has important applications around planning for savings, planning for investment, for pensions, and also for setting premiums on insurance policies, so key areas in which we work. And you'll recognize as I go through some examples, you'll recognize some links to, particularly to geometric series that you've seen already at school. And so a lot of what we're going to be seeing in this video is an application of geometric series. So we're going to look at investing some money. I'll talk you through some examples. And then there's some questions at the end of the video that you can work on your own that build on what you will have seen in this video. So we're going to invest £100 now. We'll think of it here as investing in a bank account, but it could actually be investing in a different type of asset that gives you an investment return over a period of time. We're going to assume we can get an investment return of 4% a year. So we invest in £100 now. How much will we have in a year's time? Okay, so have a quick think about what you'd expect that to be. £100 will grow by 4% over the year, and so be worth £104 at the end of the year. So let's extend that. How much will it be worth after 5 years? Well, it's the same sort of idea. Each year it grows by 4%. So after 5 years, it will have grown by 1.04 to the power 5. Okay, now you'll see a term as you go through the course of compound interest, but you can get the idea of here. Compounding, each year it grows by 4%. Okay, for 5 years. So after 5 years, we'll have £121.67. Okay, and more generally, we can do the same thing. After a number of n years, we'll have 100 times 1.04 to the power n. Okay, so make sure you're comfortable with that first step, and then we'll extend the ideas. So let's look now, rather than one investment that we're making immediately, we're going to make an investment each year. We'll make an investment now, another £100 in a year's time, 2 years' time, 3 years' time, and 4 years' time. So we're going to make a total of 5 payments. And again, we'll assume a 4% investment return. So question, how much will we have in total after 5 years? Again, you might like to just pause the video, have a think about that, and work out what you think the answer should be, or how to get to the answer. So something you'll be told throughout the course is that this sort of situation, draw a diagram of what's going on. Okay, so we're making payments of £100 each at time 0, so immediately, a year's time, 2 years' time, 3 years' time, 4 years' time, and we want to know how much we would get back in 5 years' time in total from those 5 investments we've made. So a way to do that is to look at each of these payments we've made separately and work out how much each of those would be worth, each of those separate payments would be worth, and add them all together at the end. Okay, so that first payment gets 5 years worth of interest. So we know that payment itself will have grown to £121.67. The one we made a year later was when you got 4 years worth of investment return by the time we get to t equals 5. So that will have grown to 100 times 1.04 to the power 4, so £116.99p, and so on. The one we make at time 2 will have got 3 years worth of growth. The one we make at time 3 will have got 2 years worth of growth. The one we make at time 4 will have got 1 year's worth of growth. So we can add together those 5 separate amounts, and we'd see that we get £563.31. Okay, so we've invested over a period of time of £500, so 5 £100 amounts, and it's grown to £563.31 in total. How do we introduce the idea of geometric series into this? And can we find a neater way? If we've got another problem, we've got 20 years worth of payments, how would we do that? Ideally, without having to add up 20 different separate amounts of investment. Sum, if we hadn't evaluated each of the amounts earlier on, we could see that we could write out each of the 5 payments in terms of the growth. We had the £100, and then we had a growth rate 4% for 5 years on the earliest payment, and for 4 years on the next one, 3 years on the next one, and so on. And you should recognise what's in the brackets here as being a geometric series. And hopefully you remember how to calculate the sum of a geometric series. If not, look it up, and there are some links in the blog to remind you, to some material to remind you how to work with geometric series. So we have this formula to work out sums of geometric series of a 1 minus r to the power n over 1 minus r. So a is the first term, so the 1.04 to the power 5. What's the common ratio here, the r term? Well, as we move from here to here, we are dividing by 1.04, okay, or multiplying by 1.04 to the power minus 1. So our ratio, the r term, is 1.04 to the power minus 1. So the sum of this series here, we've got the £100 outside, the a, 1.04 to the power 5, 1 minus r to the power n. So r was 1.04 to the power minus 1. Put that to the power 5, we get minus 5 here, and then 1 minus r on the bottom. Okay, so that gives us a way of evaluating this sum and this amount of money without needing to calculate each of these terms individually and add them up at the end. And we can simplify that sum a little bit. So what I've done here is two things actually. I've multiplied through, I've multiplied through here by 1.04 on the top and the bottom of the equation. Okay, so on the bottom, 1.04 times 1, and then minus 1.04 times 1.04 to the power minus 1 gives us 1 on the bottom. On the top, we've got this factor 1.04. I'm multiplying through on the top, and then I've multiplied out this set of brackets here as well. So multiplying out the brackets is giving us 1.04 to the power 5 minus 1 on the top. Okay. Now on the bottom, we've got 1.04 minus 1, which is 0.04 on the bottom. We could multiply out this bracket as well on the top, but I'm going to choose not to here. Okay, so what we've got is we've used the geometric series to find the sum of the invested amounts from the different years, and then we can evaluate this formula to give us 563.31 rather quicker than having to multiply out each term separately. Okay. So you'll see formulae looking like this as you start to study the course. You'll see them in slightly different a slightly different format. We'll arrange them slightly differently, but they are the same formula, and you'll see some different notation to represent these types of equations, these types of formulae. So make sure you understand what's going on there. And then there's some extra questions you can have a think about, which build on what you've just seen. Okay, so the first one is to generalize what you just saw. We started with 5 payments made each year of £100 at a 4% interest rate. What if we generalize that? We'll have an amount P each year being invested at times 0, 1, 2 up to n minus 1, and we'll have a general investment return of I% a year. So what's the general formula for how much money we have when we get to time n? Okay, so you can do that by working through the previous example, but generalizing each of the terms to build a general formula. We can then also change the conditions slightly. So question 2, rather than investing £100 once a year, we're going to invest £50 every half year. So we're going to make a total of 10 of these payments. So in total, we'll still have invested £500, but the timing has changed. Rather than 0, 1, 2, and so on, it will be 0, 0.5, 1, 1.5, and so on. We'll have the same interest rate, 4% a year. How much will we have in total? So here, again, you can go back to the previous example. You've now got 10 different payments to look at. And again, you'll get a geometric series, a slightly different geometric series this time. You should be able to sum that geometric series and get a formula which you can then evaluate for the total amount we'll have invested at time 5 for this situation. And again, on the course, you'll see lots of variations of this. What if we invest every month rather than every 6 months or every week? Okay, and we can see how those formulae will vary according to how often we invest. So reverses the idea of investment, and rather than saying we invest a known amount and how much will we have at time 5, this one is saying, suppose we want to have $300 at time 5. We're saving up for something that we know is going to cost us $300. How much should we invest now in order to get to $300? Okay, you'll see it's a very similar problem to the one the very first one we looked at, of investing a single amount of money now. How does it grow? This one is doing it the other way around. We know what we want it to grow to. How much money do we need to start with? So it's going to be less than $300, we know, because if we invested $300 now, we would end up at more than $300. So we can invest a bit less than that, but what's that amount? The final one extends that to investing regularly. Suppose we want to get to $300 at time t equals 5, 4% interest rate. We're going to invest the same amount each year at time 0, 1, 2, 3, and 4. How much should we invest? What should that annual amount be that means we will end up with $300 at time t equals 5? Okay, and if you've done all of those, you can think about some other examples. Could we make some general formulae for situations 3 and 4? Or what if we were investing in situation 4? What if we were investing every 6 months or every 1 month? How would that change the amount and the formulae that we're using? So those examples will give you a good introduction to the sort of problems you're going to be looking at in financial maths in the first term and in the second term, and you build on those ideas in the second year and later through the course. So I hope that's been helpful. If you want to drop me a line with what you think with your solutions to those problems, I'm very happy to have a look at them. My email address is in the blog. So thank you very much.